Okay, so we're almost getting started. Stay adding people here. Okay. Giorgio, were you able to, maybe we'll talk about this later. Don't worry.
Okay.
Mm. Yeah, one more minute and then we get started. Do you want me to share the link? Let's see. Okay. Oh, I need to admit people here. Give me a second. Then. Okay. And I'm going to share my screen real quick so we can get started. Joshua, can you see my slide?
Yes. No, actually, I'm seeing what I'm seeing is the edit bill. It's not full screen. Yeah,
Right now, you can see everything?
not good. Yes.
Okay,
Yes.
awesome. Okay, thank you everybody for joining today's 23rd edition of CONGA meeting series. We do meet here every month, and here we try to understand why we are doing this, what we are doing for CONGA. And I'm going to walk us through what it means in a short while. But today we have the privilege to have Dr. John Bosco Habarulema in our Kunga meeting today. He's a very good friend of mine, and he'll be introduced. If I have Dr. Shigo here, Dr. Shigo will be introducing him. But if I don't, I will introduce him myself. So today we have, besides the Dr. John's presentation, I think our normal announcement is that the proposal for CONGA is getting kickstarted. We are collaborating with the University of Lowell, the space laboratory there. Giorgio is here, is one of the leadership in that institute or in the lab that help us to get this on board. And next month, we're going to have Dr. Ivan Gaikin to present uh, about these own instruments across the globe. So that is an important presentation you don't want to miss. next month. So, and Dr. Gaiki is one of our leadership now that is leading this in UMass Lowell. And we're also collaborating with LDI. Um, they are the expert in instrument design, so or the instrument development. So they are going to be joining us on this effort. And we had our first meeting last 2 weeks or last week. So we are meeting every 2 weeks to discuss progress and way forward on our proposal. So that being said, this meeting is what we do regularly. And if you have, we want to make it an open discussion. Dr. John is an open person. He wants you to ask questions from him. So he will tell you if he allows you to raise your hand or just jump in to ask your question, or after the whole presentation, we usually have 15 to 20 minutes of discussion. So we can maximize that. And let me see our website. You can see our website there. And if you want to also present your work, you have some instruments you are working on. You have some ground-based instrumentation, space-based instrumentation that people can learn from your results or from your methodology. Yeah, just contact me or complete a form on the website. There is a form on the website that you can complete, and we will fix you to the next meeting. Right now, I think we have May, June already picked. I mean, already no longer available, but August, I think we still have August open. So let's see how it goes. And with that, I will quickly introduce a little bit of what we do in this meeting, because this is very important. We want to build a network of people that can work together, because in the past, a lot of mission has failed because of the ground or background um, collaboration or efforts that are missing. So the purpose here is to get to know people that we are going to be giving these instruments, because it's going to be a unit, a autonomous unit that can be plug and play. So we want to get to know people. We want to educate people on how to use this instrument and how to actually use it for their students to make it function better. So once the proposal has been approved and we have the grants, we can launch very easily and smoothly. So one of the reasons why we do this meeting is that um, we want to have this network of people. We also want to train, and we also believe that this meeting is for the training and development of members for ground-based instrumentation, like I said, installation and data usage. So people that come here to lecture us, they are pronounced engineers, researchers that have been using instrumentation in their work, and they show us results. Some of them actually put us through how this instrument work. Also, we want to ensure the distribution and accessibility of available data. So there are um, some belief that some data are available, but people are not allowing access to those data. So one of the things that we preach here is that data should be made available for science purposes, and that is why we are also putting together this large amount of data, which can be co-located with other instruments in the future, so that all of these data accessibility problem can be bridged. So particularly around the equatorial region where we have large land mass. So those are the things primary things that we do on this meeting. And as you know, we usually have special guests, invited guests that come once in all this um, once a month to give us um, some educations that we need. we believe that we need on this platform. So today we have the privilege to have our own Dr. John Bosco. And I think Dr. Shigo is around. Let me stop sharing my screen. Let me see if he's around here. Dr. Shigo, can you come online? Okay, I think Dr. Shigo is here, and I will leave Dr. Shigo to introduce our guest speaker for today. Let me reshare my screen. I think I have the bio for our speaker with me. Dr. Shigo, please. We can't hear you. Can you talking? Maybe you are muted. Hello? George, can you hear me?
Yes,
Okay.
yes.
Okay, I think I will do into introduction myself. Maybe Dr. Shigo is not able to. I usually want someone else to talk on this rather than me talking all the time. So let me see if he is able to talk. Otherwise, I will do the introduction. Okay, so um since I'm not able to get Dr. Shigo online, I'm going to do the introduction myself. Dr. John Bosco, as I said, is a very good friend of mine. And I think I met him way back in 2013 hello? In 2013 at one of the Beacon Satellites Symposium. And we were very young at that time. I think we are still young, right, Dr. John? We are very young and young researchers, students, if you can call it student, yes. I was a student, master or PhD student at that time. So, but John has grown to be a very pronounced researcher, senior research scientist at the South African National Space Agency, SANSA, widely known as SANSA. He is a visiting professor at Rhodes University and an extraordinary professor at the Northwest University, both in South Africa. His research interests include ionospheric modeling, low-latitude electrodynamics, and studies of traveling ionospheric disturbances, especially during geomagnetic storm. So Dr. John is also a professor that has trained so many students. A lot of students told me uh, what they have learned from Dr. John. And sometimes I have some people that I send to him and they are very positive about him. So today we are very privileged to have Dr. John show us some of their works, So Dr. John, the floor is yours and please share your screen.
Okay. Thank you very much, Jonah, for the kind introduction. So I'll share my screen. Can you please unshare yours so that I'm
Yes,
able to share mine?
give me a second here. Good.
I hope you can see my screen. Can you?
It's coming up now. I want to say that your talk attract a lot of people for today's meeting.
It's very good.
Yes, I think
So,
you are sharing your screen now.
okay. All right. So can I go ahead?
Yes, please.
Okay. So once again, thank you for the introduction and thank you for inviting me to give this presentation. It's also a pleasure to see a number of colleagues joining. I've seen a number of people friends, colleagues in the field. And I've seen some of the co-authors of the work that I'm going to talk about. I saw Dr. Daniel Oko, I saw Dr. Valence, and so they will help also in answering some of the questions that you may have or the audience may have. So yes, indeed, as you said, we met in 2013, and I think you were still a student. I had completed my PhD in 2010 already.
You are still
So,
a student too.
so, so you were still young, you were a student, but I had completed that time. But anyway, that doesn't matter. Uh, so today, I would like to speak about the current work that we are doing. It's sort of a progress because this work can always be improved based on the understanding and if we get additional data sets to include into our modeling approach. And so the title is Global Equatorial Latitude Vertical Equal-Speed Drift Modeling. And since this is a CONGA meeting, I'm trying to go to the next slide. It doesn't seem to be working.
Yeah, click on this slide. Probably, yeah.
Yes, can you see the next slide for me?
Yes.
Okay, so as I was saying, since this is a CONGA meeting, I thought I would do first provide a context of how the work we are doing fits into the CONGA efforts.
Awesome.
And so on your left-hand side, I think, if you can see my cursor, as you know, the role of CONGA is to try and deploy some GNSS receivers, especially of the African region, which I have circled in red. Now, on your right-hand side, let me just mention that this figure was generated in 2018. But while it may have changed a bit, the picture still remains the same in the African region. Now, on your right-hand side, it's a figure that I have taken from a recent publication by Reddy, 2025. And what they were doing here, they were using TEC, the total electron content, to try and predict or model vertical plasma drift. So in essence, what one can say is that one of the aims of the CONGA is to try and get data that will allow us derive TEC data. Once we have an accurate TEC database, then we can work backwards and use that TEC to model equatorial vertical plasma drift. And I think this is an important contribution that CONGA will have done. So the success of CONGA will actually be my own success too. Now, what the paper did, this one of read in 2025, was to rely on the global ionospheric map TC products. And they used the JPL products to try and model vertical drifts. And the drifts which they are using are coming from the NOFS, which is also the satellite that we're using for our own work. So in a nutshell, this is how the work we are doing could fit in CONGA efforts, but there are other things that we can talk about as we'll see when we are proceeding forward. Now, those who know how this vertical drift data is obtained or how it is measured, if there are some instrumentation people online, will know that generating a model that is based on data, which we call empirical, data-driven, is a very complicated and perhaps a challenging task given the amount of data that we have. And so on top, you are seeing a figure that was generated using the CHAMP data, electron current densities from about 2,600 passes, and that was aggregated between 11 to 13 local time. And what you are seeing there is a nice follow-up of the current density over the geomagnetic equator. Now, on the bottom one, you'll see the incoherent scatter radars, which are the primary instruments that give us vertical drifts from the ground. And as one can imagine, the one that is continuously running, that has a lot of data set in this kind of aspect is the one which is located in Peru. There is one now in China called Sanya, but if we come the African continent where CONGA is supposed to be deployed. We do not have an current scatter radar. So we need to bear this one in mind, that this is what we're working with towards trying to come up with the model of vertical drifts. But let's first explain what these vertical drifts are. So I adopted this kind of cartoon illustration from the paper of Anderson in 2004. And we are working during local daytime, so it's from 6 to 18 local time. So we are working within the E region between 100 and 110 kilometers. And as most of you will know, we have a natural system, the solar quiet wind dynamo current system, where you have a combination of neutral winds, semi-diurnal tides, diurnal tide, and the SQ current is caused by winds as a result of differential heating of the atmosphere. Once you have that differential heating of the atmosphere, you set up a current system within the A region. That current system itself is going to lead to an eastward electrostatic electric field, and that electric field is from dawn to dusk in low latitudes. And because of the geometry, the orientation of the Earth magnetic field over the equator, it's almost horizontal. So you have perpendicularity condition, and you now end up with vertical E cross B drift. So it's essentially Lorentz force. But that original eastward electric field, which is perpendicular to B, creates what is called the Hall current. And the Hall current which is created gets carried up by moving electrons, and that results into a stronger polarization electric field. And that stronger polarization electric field is the one that is responsible for generating what we call the eastward electrojet. So equatorial electrojet current, which flows within about 3 degrees from the geomagnetic equator. And I'm emphasizing on this equatorial electrojet because it's a foundation that we use to derive vertical drifts from magnetometer data. So what's the role of these vertical drifts? They play a number of roles in different physical phenomena. And if you can see my cursor, I'm going to explain on this figure of 2001. I took this one from a paper which was published in 2006. And the bars are showing the percentage occurrence of scintillation. And then the lines are showing the monthly mean per-reversal E cross B drift. So we have one of 2001, and then we have a figure of 2004. And in both cases, when you look at the annual statistics, you see that there's a one-to-one correlation between occurrence of scintillation and monthly mean per-reversal vertical drift in both solar activity periods. So 2001, high solar activity, 2004, approximately low solar activity. Then we look still on your left-hand side, but on the bottom panel, I took this one from a paper of 2025 that was looking at the response of topside ionospheric response during the super geomagnetic storm of 10th to 11th of May 2024. Now, in absence of a storm or any forcing, whether it is the external forcing or internal forcing, that is of significant magnitude to change electrodynamics, what we expect to have is the black curve. And when you look at the black curve, it's a figure of electron density as a function of deep latitude. And so you can nicely see the crests of the anomaly in both northern and southern hemisphere. And when there was a storm, then you see how those crests moved towards mid-latitudes in both northern and southern hemisphere. I guess an explanation of only one panel is sufficient for this purpose. And so what I'm trying to put across is that the changes in vertical drifts, changes in electrodynamics are going to affect the dynamics of low latitudes. Then on your right-hand side, there is a figure that has a color code. The color bar is the differential TEC. And what was done here is to look at the contribution of changes in vertical drifts to the launching of gravity waves. And we saw it is possible that when you have changes in vertical drifts, you have some kind of interaction between ionized component and the neutrals. And through that frictional heating, you can generate gravity waves which result in TIDs during storm conditions. And of course, on the bottom, it's what we all know, that the changes in the vertical drifts are the ones which are responsible for the formation of the equatorial ionization anomaly. And so in summary, vertical drifts modeling has a number of benefits, and they are not limited to what I've just said here. We are not the first ones to attempt to do this. There is already an existing modeling framework that was done sometime back in 2008 by Bella Feyer and colleagues. And they developed a vertical drift model based on quiet time data from Republic of China Satellite 1 observations, ROCSAT. And that data was from 1999 up to 2004. And so this model is very widely used. And for those who run the International Reference Ionosphere model, you will know that it is one which is incorporated within the IRI. And so sometimes we use it interchangeably. We say it is IRI model, but in actual sense, the initial setup is the Bera-Feyer model of 2008. And so you see the climatology, the changes in the vertical drifts for different seasons. And so we already have a reference to say, if we are attempting to do this one from scratch, does it reproduce what is expected? Because we already have a basis for comparison. Let me remind ourselves about the data sets we are using. This one, this figure from Zhang at MIT is showing us the current instrumentation in terms of synchronous scatter radars, and we can see the data is thin on the ground. So now what have we used? The first data source is the synchronous scatter radar. And the synchronous scatter radar, as I've already talked in the introduction, the only place where you can find long-term data set in Jiquilpan in Peru. And so the data that we are using is from, I think, 2000 up to 2016. And the data comes from the mode which is called the Jiquilpan Unattended Long-Term Studies of the Ionosphere and Atmosphere, the FRIA mode. And that FRIA mode is the mode which looks at E-region echoes, and it has been shown that that data set is a very good proxy for the F2 region vertical equal-speed drift measurements. And so you start from the equatorial electrojet. We know that EEJ is related to ionospheric conductivity, and so we can write a direct relationship between equatorial electrojet with the electric field, and this sigma is the conductivity. And within the E region, conductivity itself is directly related to electron density during local daytime. And so one can safely say that the conductivity is directly proportional to the maximum electron density of the E region. And of course, the maximum electron density has a direct relationship with the solar activity. And so conductivity itself is directly proportional to any indicator of solar activity, whether it's F10.7 or sunspot number or any other indicator that one could choose. And so one can do a mathematical summary and say, if you have electrojet, it's proportional to vertical drifts. Now, for any quantitative study or any modeling, one can safely say once again that the solar activity is going to be a very big indicator of how the vertical drifts are going to change with time on a long-term basis. But as you know, sometimes you have an established understanding and the measurement tell you something else. So sometime back in 1973, Richmond did a study that showed that for quantitative studies and modeling of vertical equal-speed drift, the changes in H component, which is a representation of equatorial electrojet, was proportional to vertical equal-speed drift. And in fact, the changes in delta H and NME, the maximum electron density in the E region, had a direct relationship to the extent that an increase of 10% in one led to a similar increase in the other parameter. But what happened in 2008 up to 2010, which was the extended solar minimum, and I refer you to the figure here and look at the vertical red lines. Elsewhere, during the other phases of the solar activity, the blue dots, which is the vertical equals speed drift, and the black dots, which is F10.7, do correlate. There is a linear correlation. But during the extended solar minimum, that correlation did not hold. And so that tells us that there should be other factors which are driving changes in vertical drift itself, not necessarily on the solar activity. The second data source we use were satellite measurements, and we are using the Communication Navigation Outage and Forecasting System, in short CNOFS. The satellite was launched in April 2008, and you can see the altitude it covered, 400 up to 800 kilometers. The period was about 97 minutes. And so because of that, it was taking about 90 to 100 minutes to return to its original position in its orbit. And so because the satellite is moving, it does not sample continuously over one location in terms of time. And in most cases, satellite data is very good for climatological studies, not day-to-day variability of a particular parameter. Now, below 550 kilometers, all local times can be sampled in 6 to 7 days. And we know from previous studies that within about 400 to 550 kilometers, the data, the IVM ion drifts, the ion velocity meter ion particle drifts are approximately equal to vertical equal speed drift at about 400 kilometers. But when we are doing this kind of modeling, you want to look at what is changing over a particular location. But the data itself is coming from a satellite which is moving. Now you need to do some kind of consideration to approximate the spatial resolution over your area of interest. I can hear someone talking. Does someone have a question?
No.
No? Okay, so I'll proceed. And so what we do is that if we are looking at one location, we limit our data to be within plus or minus 5 degrees geomagnetic latitude, and then the geographic longitude around that location is limited to plus or minus 7.5 degrees. And 7.5 degrees is chosen deliberately because this is a 15-degree variation. And within 15 degrees, we do not want to change local time a lot. Otherwise, we change electrodynamics over a particular location. Now, on the top, on your right-hand side, we have data for CNOFS over one location, Addis Ababa, which is the equatorial location, 2011. And on the bottom, you have similar data set, but now over Hicamaca in Peru. And so in essence, if you look at the entire year, that's the data that you're working with. And that's a data set that forms the basis for the modeling we are going to perform. And so it tells you where you are lacking and where you are going to do some kind of trade-offs during your studies. The third one, data set, is the ground-based magnetometer observations. And from the ground-based observations, magnetometer data, what we can derive from it is the equatorial electrojet. And we can derive that based on the differential magnetometer approach, which is well known, it's well established. And this global map where my cursor is showing us where we have stations, one at the equator and one which is displaced by about 6 to 9 degrees away from the equator. And that is approximately the pair that allows you to estimate the equatorial electrojet. And the mathematical formulation is straightforward. If you have a magnetometer station that is at the equator, it's going to observe a number of current systems. I have listed them here from 1 up to 6. There could be others, but they may be minor. Then if you have the one which is off the equator, that is outside that band of plus or minus 3 degrees, but does not exceed 6 to 9 degrees away from the geomagnetic equator, it's going to respond to a number of these current systems in the same way because these magnetometer stations are close to each other. But the one at the equator is going to have an additional contribution which is coming from the equatorial electrojet. And therefore, if you do a direct subtraction of the magnetometer measurements, the one from the equator, subtract the one off the equator, you remain with the representation of the equatorial electrojet. And that is what we call changes in the H component, delta H. And when you look at the figure, which my cursor is on, we have delta H plotted as a function of vertical drifts. This figure was generated in 2004 by Anderson, and you will see that you have one-to-one correlation. And therefore, if you have delta H, you can actually mathematically derive vertical E cross B drift. So that's the third data set that we are using in this work. Now, the caveat here is that the technique is only applied only during local daytime, simply because the currents are too weak during nighttime to be detected by magnetometers. And so that's the only drawback that you have when you are deriving your vertical drifts using the equatorial electrojet as your benchmark. Now, let's now look at the data coverage that we are going to use. We are going to use the incurrent scatter radar from about 2000 up to, I think, 2016. Then we have CNOFS data that goes from 2008 up to 2015. And then we have magnetometer-based data set that is approximately from 2008 up to 2019. But each data set has its own merits and demerits. The incurrent scatter radars, it's only one, and so you only have one longitude sector that is represented. It is very expensive, both in operational costs and even deployments. You have low Earth orbit satellites, very attractive, but as we have seen, they can only be very reliable when you are doing climatology studies. Ground-based magnetometers, you can only get an inference of vertical drifts during local daytime, and so you miss the nighttime. Okay, so first thing that we do is we want to derive a relationship between the equatorial electrojet and vertical drifts. And for this purpose, we are relating EEJ and CNOFS vertical drifts. Now, we need to bear in mind a number of considerations that when you do this, you need to do it over a location where you can be able to validate your approach. And the location that is naturally chosen is the one that has independent data set that can be used to do independent verification of whatever mathematical algorithm has been developed. And so we went and started from working in Hikamaka. Simply because we have a magnetometer there, we can constrain our CNOFS vertical drifts over that location, derive the relationship, and validate it using incurrent scatter radar, which has not been used in mathematical derivation. That's what this figure is showing you where my cursor is. Then in the middle figure here, we are showing changes in the H component over Hikamaka and Pura, which are the two magnetometer locations which allow you to do differential magnetometer approach. And then in C, the one which has a red curve, we are showing delta H now, which we've obtained by getting the black curve, subtract the blue curve. Then the black dots are the CNOFS vertical drifts. And you'll see that although they are not one-to-one, they have the trend. The trend is correct. And therefore, we have a basis for linking EEJ and CNOFS vertical drifts. And again, I'm reproducing this figure here because these are the locations where we can carry out to this kind of formulation. So what do we use to do this? We are using machine learning. And so we use artificial neural networks, and it is a presentation on its own. And so I'll try to simplify it as much as possible. And I prefer to sometimes think of it in terms of regression modeling, although it's not necessarily that, but one can write an equation in form of that. So you have a multidimensional input space. In this case, we have X, which ranges from X1 up to Xn of dimension n, and you have an output scalar quantity, which in this case would be our vertical drifts. So you can write it according to equation 3. So these X here are going to be our inputs. Then this A in equation 3 is what we call a continuous nonlinear function. And so in machine learning, it's called an activation function. And you'll see that we have parameters such as Wi, Mij, and Ci. And these are weights. So Wi and Mij are weights. And C is a bias vector. And in machine learning, we call these ones free parameters. And for you to know which one you need to use, you need an optimization function to be able to do that. So the way one would feed the data into this equation 3 is that you have your input X that undergoes linear transformation by weights M and bias vector C. So that would term it as matrix to vector multiplication. Then the resulting new vector from this linear transformation is going to go into the activation function A. And then the procedure, these two procedures are going to be repeated H number of times with the different weights M and biases C. And this H is also a free parameter, which is called the number of neurons. So you hear people saying, how many neurons did you use when you're doing the mapping? And so the outcome of these processes, so the H results of this activation function are the finally linearly combined through weights Wi. And so for you to be able to do this, choosing weights and biases, you need what is called a training algorithm. And for this case, we are using Bayesian regularization backpropagation algorithm. I'll provide a reference where everything is for those who are interested, because we can spend more time discussing this than anything else. Anyway, let's now discuss how we do the mapping. So I have a cartoon illustration here of the mapping process. We have an input layer, we have a hidden layer, and we have an output layer. This input layer is the one where you feed all the inputs of the parameters which influence whatever you're trying to do the modeling. And in this case, we have diurnal variation, we have seasonal variation, we have different magnetic indicators, we have auroral index, we have auroral electrojet index, we have KP, we have symmetric component of the ring current index, high resolution DST, if one would like to call it that way. We have F10.7, and we have delta H, and this is the electrojet. Let me go back and say that we are linking electrojet to NOFS E cross B drift. And so the main input here is the changes in electrojet, which is represented by delta H. Having done that, let's look at how each and every input we are putting in is contributing to the performance of what we are trying to do. And that's what this bar graph is showing. So day of the year is representing seasonal variation. Hour is representing diurnal variation. SYMH, AE, and KP are all indicators of geomagnetic activity. F10.7, of course, is solar activity. And the EEJ, the equatorial electrojet, is the one we're trying to link to vertical drifts from NOFS. And you'll clearly see that it contributes more than 35% to the variability of NOFS E cross B drift. Once we've done the mapping, then we look at how the models are performing. And to do that, we usually divide this into different data sets. In this case, I'm showing a figure of a training data set and a testing data set. And then you look at the coefficients of determination. If you look at what the model is predicting as a function of the actual data for both training and the testing data set, you see that the coefficients of determination values are almost the same. This is important because you want to make sure that your model is not overtrained or is not undertrained. And so these values should be as close as possible. Having done that, let's test it on a completely new data set that you've not used in your model development. And with that, we turn to encoded scatter radar, and then we test the algorithm. And that's what we are showing here for 2009 and 2013. So remember, we are using a Fourier mode, which is based on the echoes from the E region. So that is on the x-axis, and on the y-axis, we have what we are calling the reconstructed vertical equals B drift, now from the machine learning algorithm. You look at the correlation coefficients, and one can say 0.73 from 2009 and 2013. These are different phases of solar activity. It's a consistent performance. But there may be an argument that perhaps that correlation is very small. It could be having some merit, but we need to remember that you are comparing data that is taken within the E region, which is Fourier mode, with data that you are reconstructing from CNOFS data set that is at about 400 kilometers. And so you need to bear in mind that there's a bit of height difference. And so in our own view, this is a good performance. Let's look at climatological comparisons and see how this works. So now let's test over different longitude sectors. And in A here, we are showing data in May 2012 over Cajamarca, which is in Peru. On y-axis, we have vertical equal speed drift as a function of local time. The black dots are showing coherent scatter radar. The blue dots are showing CNOFS vertical equal speed drift, which is the basis for our reconstruction. And the black dots are showing the reconstructed vertical equal speed drift. And we think climatologically, we get the trend. You go to part to figure B, that is over the African sector. The other one was American sector. African sector, we work over Addis Ababa. Of course, we don't have an current scatter radar, but we have CNOFS vertical equal speed drift, so we can do that comparison. And once again, the approach is limited to local daytime. That's why it's not, the night time is not covered in African sector. We move to Asian sector and we test our algorithm over Phuket in Thailand. That is the trend. And now if we have that, let's look at the benefit of doing the reconstruction. We started with a very sparsely populated data set, for example, in 2011. And when we now superimpose the reconstructed data set from EEJ, equatorial electrojet, that's the data that you get during local daytime from 7 up to about 17 local time. So look at the benefit, how much data one gets out of that reconstruction. And so we think we can reconstruct vertical equal speed drift during local daytime based on magnetometer measurements. Now that we have all the data in the same format, we can now develop the global comprehensive model for vertical equal speed drift. And that's what this cartoon illustration is showing. So this is the model architecture that I'm going to now describe the outputs. I don't know how much time I'll have, but let's look at this hidden layer. So the hidden layer, you'll see, I talked about the number of neurons. So you vary them from 1, we vary them from 1 up to 100 in steps of 1. And then with that, you compute some kind of metric, and that metric we are using root mean square errors. And that's what we have here. And then we do the ensembling. The ensembling means that you train so many modules and you average, and then you take the best ensembled result. And let's look at the performance of the model in different years. We are looking at 2002, day of the year 75 at 12 local time. We are choosing 12 local time. Again, it's intentional because during that time, we expect vertical drift to be positive almost in all longitude sectors. And if you look at 2002, that's what the vertical drifts are. Look at the color code, they are positive. Go to 2008, the picture seems to be consistent. Go to 2014 and go to 2020. So vertical drifts are positive. And so I think this gives us an initial confidence that one may be in the right direction. And of course, to put it in perspective, look at the indication of the solar activity that we are dealing with for those plots. Let's look at annual results. Now, in these annual results, I'm going to be comparing with the Bell-Fager model, which is incorporated within the IRI. So when you see IRI 2020, it's essentially that model that was developed based on locusite data from 1999 up to 2004. Yes, 2004. So we show results of American, African, and Asian sectors. So if you look at the first panel, this is in 2012 IRI. So A in Hikamaka, 77 degrees west. Right at the bottom of that, which is panel B, it's showing the model which you have developed over the same location. Then you go to the middle panel, C, that is showing the Bell-Fager model over Addis in African sector, and part D is showing our model over the same location. And part E is looking at the performance of these models over the Asian sector, in this case in Phuket, 98 degrees east longitude. And so the other one is 2012 results, and the other one is 2022 results over the same sectors. One can make a number of deductions from these figures. Number one is that our model tends to be reproducing some finer details of what could be changes in vertical drifts. But we need to bear in mind, this is climatological. But nevertheless, you see these kind of finer details which are not present in the original climatological representation within the IRI. And that picture seems to be consistent irrespective of the solar activity, because when you look at 2012, look at 2022, the picture is consistent. The other one that one can derive from this is that the vertical drifts are higher in the Asian sector than the African and the American sectors. And again, that you can see it from 2012 and 2022 data sets. But I think one of the intriguing observations is this one over Hikamaka. Look at this on the left-hand side, panel B. This is a function of local time. And this you are seeing vertical drifts which are positive post-midnight. And for those who are in this kind of field, one will have a number of questions about this. But in 2012, we are seeing that over Hikamaka. In 2022, we are seeing the same observation. That observation seems to be largely absent, or it's not well pronounced over the Asian and African sectors. So we need to bear that in mind for future discussions. And so the question which we asked ourselves when we saw this was, is it real? And at first we thought there could have been perhaps an error in modeling, but when we looked at literature, then we found some papers which were published. This one was published in 2016. And what the authors did was that they looked at a model which is called whole atmosphere model and coupled with the global ionosphere plasmasphere model. And when they ran that, it successfully reproduced these unusual nighttime upward drifts. And I would like to draw your attention to the longitude sector that we are talking about. Hikamaka is about 77 degrees west, and so that would be around here where the arrow is pointing. And look at the local time that these authors dealt with. This is from 0 up to about 4 local time. That's exactly where we are seeing the positive vertical drifts. I think in the interest of time, I won't go into the other one, but one could also compare with what the others did with the SAMI 3, which is another model of the ionosphere, theoretical, coupled with work marks. And again, these authors also could reproduce these upward vertical drifts post midnight. So nighttime data set is showing you that one could have vertical drifts which are positive, but the observations don't show it. The observations which exist in Ikamaka are not showing this. So there is a lot that perhaps we still have to learn. Does that mean there's some kind of physics which is missing in the current model formulations? That is an area that one can pursue for further investigations. Now, the model has been developed. We've looked at whether it's reproducing climatology based on what is existing currently. But we needed another data set that was never used in model development. Of course, one could say the incoherent scatter radar, not in Fourier mode, was not used. But again, it was over a location where we had used the Fourier mode in model development. And so to try and find the independent data set, we turned to ICON's IVM dataset. And IVM dataset for ICON was running from, I may not know the dates very well, but I think it was from 2020 to 2022 or somewhere there. But in the end, we ended up using 2022 dataset because the other dataset, the solar activity was too low, and so the dataset itself was contaminated because there was no sufficient electron densities for one to be able to accurately derive the vertical drifts from the IVM dataset. Anyway, we need to remind ourselves that the model we are trying to validate is using magnetometer derived data from 2008 to 2019. It's also based on NOFS dataset from 2008 up to 2015, and it's using Fourier dataset from 2001 up to 2016. And now we are trying to validate that model using a dataset of 2022. And the reason why I'm spending some time on this is that this is extrapolation in time. That dataset was not used just in time, but also based on also different observation techniques. So what we do is we get 2022 dataset from ICON, and then we categorize the data into different seasons for us to be able to compare with the existing climatology, which is the Bella-Feja model of 2008. So we have from January to Feb, that is approximately summer. Then we have March to April, that is equinox, and May to August, that gives you solstice. And then we average the IVM drifts at 90-minute intervals. And again, we do this because that was a satellite orbital period. After dealing with the actual data set, then we go to the model data set. So we reproduce or we simulate data from our own model, and we also simulate data from the Bella-Feja model. And then we go through the same process of averaging with respect to this kind of seasonal categorization.
2 more
And
minutes.
when you,
Two,
okay, yes, you have a question?
no, two more minutes. We run out
Okay,
of time
I'm,
here.
I'm,
Sorry.
I'm almost done, don't worry. Okay, so when we do that, we now look at Hikamaka, which is the top panel, which is A. Then we look at performance in Addis, which is the bottom panels. And then we look at the Asian sector in Phuket, which is the bottom panels. And then you can compute the metric, and the metric we are using is the root mean square error. And you'll see that in most cases, the model we have developed is giving the lowest root mean square error compared to the current climatological representation, and that is if you benchmark both models on IVM drifts. And if you perform or you compute percentage improvements, then we see that we improve the current representation by about 40% in the American sector, 23% in the African sector, and 8% in the Asian sector. And so that's what we've done. And so we think that a combination of these data sets gives you a true representation with respect to longitudinal variability of ionospheric vertical drifts. And everything I've said is already published. This is a paper of 2026. For those who are interested, go and read this paper. The model details, everything has been made available on this link. Please go download the model, test it if you have data, tell us if there's some shortcomings, share with us the feedback. You can send any feedback to myself or Dr. Daniel Oko. Our emails are here, and we'll be very glad to improve the model where necessary and if it is possible. And with that, I would like to thank you very much for your attention, and I hope we have time for some questions. Thanks a lot.
Thanks for some question. It's on a question right now.
Oh, I'm sorry if I exceeded time, but
Yeah,
okay.
we do have 15 minutes and some extra 15 minutes, but you took everything.
I took everything.
Yes. But it's okay. We can still go for the loves of science. You know,
Okay.
when something is interesting like this, we allow it to go smoothly. So we can still go for 10 more minutes. If you have any question for Dr. John, who is here, please ask your questions. Thank you very much, by the way, Dr. John, for this wonderful presentation.
It's my pleasure.
Yeah. Okay.
I have a question.
Okay, go ahead, please.
Okay, so thank you very much. Thank you, John Bosco, for your nice presentation. My question is on estimation of this EJ using two magnetometer data just at the ground. So, yeah, you subtract the baseline first from the measurement of the deep equator and off the equator, and then you subtract the remaining. So, do you think this method is really reliable? In fact, let me rephrase my question. How do the solar, quiet currents and equatorial electrojet compare at the deep equator? Are they distinct, or is it simply a manifestation of the SQ current?
Okay. So thank you very much, Melissa, for your question. So if I understand you very well, you are asking about whether the methodology, the differential magnetometer approach is reliable in estimating changes in vertical drifts.
Yeah,
Okay, very good question. So you have two magnetometer stations.
yes.
One at the equator is measuring a number of current systems, including the equatorial electrojet. And among those current systems is the SQ current system. Then the one outside the EEJ belt, which is at about 6 to 9 degrees, is also measuring different current systems except the equatorial electrojet. And the assumption is that both of these magnetometer locations are going to respond to the main current systems in the same way. And so when you do a subtraction, you have essentially canceled that SQ current system. That's a main assumption. I hope I do answer your question.
Sorry, I had to mute you. Sorry because of the echoes. So yeah.
Okay. Okay. So the point is this: is the SQ current at the off equator and just at the deep equator the same?
Yes, yes, that's assumption. They are approximately the same. Yes.
Okay. Thank you. Thank you, Damasco.
You're welcome.
Any other question for Dr. John Bosco?
I have one. Can I ask?
Yes, please.
Yeah, thank you very much for the very nice presentation. I was particularly interested in knowing more about um, E cross B drift derived from the magnetometers. How reliable can this kind of information be used in being used to trying to predict plasma bubbles? As we know that when we have a certain velocity of the vertical drift can be a good indicator for spray depth occurring the post sunset time.
Okay, thank you very much for that question. Good question. Uh, as you know, plasma bubbles and associated phenomena such as spray depth are in most cases nighttime phenomena. In most cases. But these vertical drifts that we are deriving from magnetometer observations are limited to local daytime because you are essentially estimating the current system within the E region. So I'm afraid that it will not assist in studying plasma bubbles because we do not have the nighttime representation.
Mhm. Okay, thank you.
Okay?
Yes,
Thanks a
good,
lot.
thank you.
So one quick question for you, John.
Yes.
Or two. So RI, why are you using RI for your validation? Because it doesn't really seems to me that RI is giving the right, there are some things going on in that plot with RI.
Okay, quick answer. We are not using IRI for validation. We are using we are using IRI to show that what we have done is actually an improvement over what is existing. So it's not for validation. But currently, most of the climatological studies are using that model within the IRI. So what we are trying to show is that we can actually do something that is a bit improved of what is being used
Okay.
now.
Okay. So
Mm.
what are you validating your model with in short?
The icon data,
The
which is
icon.
not being used
Mm.
in model development.
Okay.
And that icon data is the one that I'm showing on this last slide, if you can see that.
Let me show it.
So the dots are icon data. The blue curves are our model, which we have developed, and the red is what is within the IRI.
Oh, wow.
Yes,
What
yes.
is going on with that pre-reversal enhancement? Like, no, both the model are not doing that, but HRI is just shooting up that every time. Do you know what is going on there?
Yes, because remember, for you to understand how this IRI is getting this, one would have to go back to the formulation of the original development of the model within IRI. So it was based on on-centric data, which was categorized in different seasons. And that's why the climatological performance seems to be repetitive only with the changes in magnitude.
Yeah,
So even where you don't have pronounced reversal enhancement, some of the models do reproduce that. And that tells you need to improve that aspect of modeling.
yeah.
Mm.
So yeah, you can see RI is very, very out of place here, everywhere. I don't know what he's doing here because if you look at the other two models, they are more or less around the same region, but RI is everywhere, shooting up.
No,
Anyways,
I wouldn't say I wouldn't say it's all that bad. It is, I think, climatologically, it gives you what are expected value, the expected trend of vertical drifts. It does give that. And it is a model that, by the way, that has been tested, that has been compared with various measurements. And so it still remains a reliable climatological model. What I am requesting colleagues who may be on this call is to please go download our model and test it so that we have a comprehensive tested model that we can improve over time. Hopefully, we can have an accurate representation.
Yeah, I think they can hear that. I believe in your model right now, giving this result. I think it's really good to test it out. If somebody is working currently on this, I think it's a good one to test your work with. We have Xiaomi. Uh, please come up with your questions. Yeah.
John, there's also a question in the chat. Okay.
Okay.
John, can you see that?
Uh,
Mm. Xiaomi
uh,
is raising his or her hand, please.
yes, I think they were saying there is a question on the chat, which
Okay.
I can't seem to. Okay, are there actually a number of questions in the chat?
Oh,
There are six
sorry.
of them.
No way. Do we have time?
No, no, some are introductions.
Okay.
Uh, okay, okay. The other one is the one of Medicel. That one has been answered. So I think there's no any other question outstanding because the one of Medicel has been answered.
Okay.
Hmm.
Yeah, so let me see if anything. If you can go to the one of the slide, first slide that show the comparison between CNOF and other African, I mean, continents comparison. I wanted to see why is African close correlated with compared to other ones.
Okay, tell me when I get there. This one?
No, no. This one. That
This
one.
one.
No. The daily Diana one that you showed. Uh,
Okay, let me guess what is it this one?
no, no, this one. Oh, you left again. Okay.
Oh, sorry, this one?
No, the Diana kind of variation that you showed to compare different continents. Anyways, if you were there and then you left again.
Okay, let me see. You tell me which slide are you seeing now?
We are okay. Oh, it's moving too fast. Okay, so we are seeing the solar
Data.
flux.
Okay, data coverage.
Yes, total coverage, yes.
Okay, you can see the next slide.
Yes.
Okay, we
I
are
think,
now talking about input output.
okay. Okay, go again. Yeah, this one. Don't
This
go.
one.
Oh.
Yes. Okay. No, no, it's already there. Is it this
You
one which is talk about comparison different years?
no, no, no. This one is the map of the world, the global map. I'm talking the one, yeah, this one here.
Okay.
So I see a lot of correlation with African sector, but look at the Asian sector. There's no much correlation here, and this one also, the American sector also shows close correlation. But what I'm saying is that is there any problem with our thing here, or is what we should believe?
How do I answer your question, John? So this, I actually wouldn't comment on the correlation unless I estimate the accuracy of the model in capturing CNOF's vertical drifts. Because all that we are doing here is to see whether the reconstructed vertical drift reproduces what is expected trend-wise,
Okay.
not necessarily the accuracy.
Hmm.
Hmm.
Yeah, it's fine. I just wanted to be sure that it's not because we have less quality of data or our data is what is actually making us the African sector more correlated here than other ones. Like Asian is really far away from this correlation. So it's just a curiosity, not thing to worry about.
Okay, that's fine, but the other consideration could be that even the reconstructed vertical drifts may be overestimating what perhaps is vertical drifts in the Asian sector. One could say that until we have actual data over that longitude sector that validates what we have done, I do not think we can reach on a conclusion about the magnitudes.
Okay,
So we
awesome.
need actual data to do the validation.
Great, great. Thank you very much, John. Do we have any other question? You can stop sharing your screen now, Dr. John. Thank you so very much for this wonderful presentation. And I'm so sorry for the lateness in time. We we have to go past the time because it's very interesting to have these kind of discussions once in a month. And next month, we are going to have another special talk from Dr. Uh, Ivan Gaikin. Is the director of Space Lab Science Laboratory in UMass Lowell, and is coming as an invited guest to present their work, particularly on global equatorial, let me see, it's going to show us what they are doing with Giro network and GNSS sensor. Giro network is a global, GSOND coverage. So he has been working on this for multiple or several years. So in his presentation, he's going to show us all these results that they have and how the instrument, the dynamics of the instrument. So that's what I wanted to just mention before we go. And if there is no other question for John, I hope there is any other question or not. We can call it a day from here. Let me see, stop sharing my screen. Okay. Okay, thank you everybody. Let's appreciate our speaker again for this wonderful talk. Thank you, John, again. Thank you very much. I will
Thanks a
allow.
lot for listening to me and for the invitation.
Yes, 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 yes. Thank you.
Thanks. Great seeing many colleagues.
Yeah, you can always join us here. I think you are a member of CONGA, and you mentioned in your talk that CONGA is doing what you really need for your work to actually blossom. So we're happy to hear that, and hopefully we can get CONGA get CONGA operative in the future time. We are working tirelessly on this, and we will see what happened. So thank you, everybody, and I will see you next month again.
Thanks a lot.
Yeah,
Thank you.
yeah, sure.
You are welcome.
Thank you,
John.
John Bosco.
All right.
Thank you for the nice presentation.
No worries. Thanks for your contribution.
Okay, John.